Hello and welcome to the first chapter, talking about chemistry. Chemistry, which is the study of matter and its changes. So, welcome to your journey here, learning about chemistry. This is the first chapter, chapter 1. So, what do you think? What is the most important idea of all human knowledge? And this is a very, very biased answer. It For chemist world, it's all about the properties of molecules and atoms. Molecules being a stable group of atoms. And I must say, I'm jumping ahead. If you don't know what atoms are, I occasionally get students that don't know what atoms and molecules are. We will cover this in pretty good detail, but most people know what atoms and molecules are. So there's, of course, other questions, very important questions as well, not just in the science world. Questions dealing with culture and history and whatnot. But for science, and sometimes chemistry is referred to as essential science, and I must say I am a very chemistry-centered person, which makes sense because I have a PhD in chemistry and I teach it. But we're going to focus much of the talks on these properties of molecules and atoms. So what are they? Well, what is an atom? And we'll talk about this more next chapter. But it's the basic unit of an element, and we'll talk about elements later on. So atoms are different for different elements, and they respond differently on how they're connected and connect with other elements. And understanding matter at this level gives you quite a bit of knowledge and quite a bit of control. And compare this before atomic theory, when we just didn't really know what's going on. And there were some confusing things that happened, like iron starts out shiny, and it becomes less shiny, and it's heavier now, so because it rusts. And of course, we know iron is a metal, and it reacts with oxygen to form iron oxide, and that's the reason why it increases in mass and that there's a new compound. But I mean, before that, how do you explain that property of iron rusting and gaining in mass? So, and I mentioned this before, atoms, these are the ultimate unit of an element. So that's what atoms are. And the original idea of atoms are actually Greek. Greek came up with that. And we don't typically see just plain old atoms in nature. We do. I mean, in the atmosphere, air is about 1% argon. Argon is a gas, and it's a single atom, so we do see single atoms. But it's not generally what happens. Typically, atoms are bound together in stable groups of atoms. We call molecules stable because they stay together, they don't fly apart. And here's an example of a molecule. Here's a water molecule made of 2 hydrogens and 1 oxygen. And what holds it together is a chemical bond, specifically an intramolecular bond, and we'll talk about this later on in the class. And science in general, to me, it answers the question why. So when I say I'm studying something scientifically, besides using the scientific method, I'm trying to understand why something happens. And chemistry specifically is the science that understands matter. So understanding matter, how it responds, how it changes, how it doesn't change, and so on. So that's what we're going to focus this class on, is matter and its changes. And they're a little bit, so small changes can have huge effects. An example of this is carbon. So if you look on this image here, on the bottom left, we have graphite, and that's the stuff that's in pencils. It's very common. And then we have diamonds. So they're both made of carbon, and graphite, it's slippery, it's black. Diamond, it has a honeycomb sort of structure. Graphite does. Diamond, on the other hand, has something called a zinc blende structure. It's every tetrahedral site in a specific fashion is called the zinc blende. Diamonds are also very hard. So whereas graphite is brittle and slippery and diamonds are really hard, graphite conducts electricity, diamonds are an insulator. So just changing the structure, same atom, just different connectivity, can greatly alter the properties of something. And In this day and age, it's called the Age of Enlightenment, and specifically, we look in terms of empirical data. Empirical means it's experimental. We observe and we have experiment. This is versus philosophy. So much of previous to the 1850s-ish, 19th century, mid-19th century, we focused most of our knowledge on philosophy. And once we switched over to empirical, the world has changed greatly. And what specifically we have the scientific method. The scientific method, and what's nice about this is it's, well, among other things, it's reproducible. It's a set way to understand something. So if something's scientific, it means it's got a system. And the system that we use for science is scientific method. And specifically, we have the steps: observation, hypothesis, experimentation, and then laws and theories. So let's talk about observations first. Observations, we also know these as data. And there's two types of observations. There's quantitative and qualitative. Quantitative means number. So anytime you can assign a number to something that's quantitative, qualitative, those are more idea-based. And for instance, so here's an example of a qualitative observation. Lavoisier, he noticed that there was no change in mass. So, well, like you can say it's quantitative by its zero, but this is the idea. So, Lavoisier then came up with the idea like, hey, matter is conserved for all chemical and physical processes, so therefore, mass, the total amount of matter does not change. And that is an observation. Well, by doing experiments, he observed that him and his wife, I should mention his wife, it wasn't just the male Antoine Lavoisier, also his wife, whose name escapes me right now, but she was heavily involved. It was a very romantic relationship. They spent lots of time in the lab together, and they were also French nobles, so they were nobility. Sorry, French nobility as well. Okay, but we have observations, and then we can come up with a hypothesis. A hypothesis is an educated guess. So, going with the Lavoisier example, or the Lavoisier couple, I should say, they came up with the idea of conservation of mass. But when a substance burns, it combines with air. And so, like I mentioned, with iron rusting, it gains mass. His idea was like, oh, maybe there's something in the air, that the air is actually made of matter. And a good hypothesis is falsifiable. So good science in general is falsifiable, meaning you can prove it wrong. So you can, by experimentation, you can prove it wrong. And if you prove it wrong, then the hypothesis is wrong. You have to modify it, or it's just outright completely wrong. So scientific law. Scientific law is a summary of observations. So the conservation of mass, there were Lavoisier and wife. They did enough work in their laboratory that they were able to say, you know what? In physical chemical processes, we're not making matter. Whatever we do, if we are careful enough, matter is not neither created nor destroyed. And so then they could use this for future experiments. So fire, we're not losing matter in a fire. I mentioned that before, like in a previous slide, that there's actually stuff in the air. When you burn wood, you're not losing mass. You're just combining it with stuff in the air, and then also the stuff coming out. Also, if you weigh the ash and you weigh all the gases coming up, you find out that you don't lose any matter. So scientific laws, you cannot choose to violate them. So this is not like a civil law. But can you break a scientific law? Yes, you can. You can under certain circumstances. You can break the law of conservation of mass. Maybe perhaps you're familiar with the equation E equals mc squared. Energy is mass times the speed of light squared. Energy and matter are interchangeable by that, and that's so that breaks the law of conservation of energy and the law of conservation of mass. But we can also explain that away. So you can see that under certain circumstances you can break scientific laws. but it's not something like, well, today I'm just not going to obey the law of gravity. I'm just going to float to work, right? So that can't happen. You can't just choose not to obey a scientific law. So theory, to use my own words, a theory is a proven fact. So when a hypothesis or a series of hypotheses you form them, and if there's enough experimental evidence to support a theory or to support them, this hypothesis or series of hypotheses may become a theory. And it is a much more general thing. So this is so what's an example of a theory? Atomic theory. It has the word theory in it. That matter is made of small particles called atoms. And we have much, and we'll talk about atomic theory in subsequent chapters of the proof for that. And atomic theory, and there was some history that atomic theory was initially wrong. So Dalton started off with it. He thought that atoms were indestructible. Turns out atoms are not indestructible. So even though a theory, there's still some things that need to work on, and they tweaked and they grow. So that's one thing with theory. So theory is a proven fact, but it's also falsifiable, but it also can be improved upon as we learn more. And all right, I just mentioned Dalton's atomic theory. And we can use theories for future experiments and to further refine the theory. So here's a picture of scientific method. So start off with observations. Observations can be quantitative or qualitative. So quantitative are number-based, qualitative are idea-based. And if there's enough observations, we can come up with a scientific law, which is a summary of observations. Observations can then be used to form a hypothesis, and then a hypothesis is tested via experiments, and then the experiments then confirm or revise a hypothesis, and then if enough data and support with a hypothesis, you can form a theory, and then you can further revise theory. Laws, so you can have some observations, and if you get enough data, and then you can come up with a law, and you can be wrong, right? I mean, it's not like you can just, every time you gather a bunch of data, you can find out it's wrong. I could have an observation like, you know what? Whenever I start a fire and if I'm camping and I'm burning wood, the flames are always yellow. So I'm going to say I have a scientific law, a summary of observations that campfires are always yellow. And then, but then you can go and you can throw some copper in the fire, and then it turns kind of a greenish blue color. Like, whoa, well, that law has been disproven. Campfires are not always yellow. So that's an example of like how you can. That's a very simple, tongue-in-cheek example, but that is one way you could prove that a law is wrong, or you can attempt to prove a law. Okay, so which of the following statements best explain the difference between a law and a theory? Law is summary of observation, theory is a proven fact. So A, that's not right. Theory, a lot of times people use theory as a speculation. Oftentimes people refer to theories as hypotheses. So, in a scientific sense, hypothesis is a guess. It's an untested, unverified guess. So oftentimes people say, oh, this is just a theory. Well, theory in science means proven fact. So A is wrong. Hypothesis is more, it's not necessarily speculation, it's an educated guess. You're like, we're really thinking about this hard. B, a law summarizes observation. A theory gives underlying reasons for them. That's very closer to the truth. Because the theory is, it's verified by experimentation. And C, theory describes what nature does, law says why. C is kind of backwards. B is the best answer for this one. Okay, what's matter? Matter is anything that has mass and volume. So definition of matter, anything that has mass and volume. So what is matter? Anything you can touch, feel, taste, smell, that's made of matter. What's not made of matter? Energy. Energy is not made of matter. So is there other things other than matter and energy? Of course. There's emotions, there's gravity, right? That's a force. That's not necessarily even matter or energy, but there are other things, of course, that exist in the universe. But matter, we're talking, and chemistry is a study of matter. So what is matter? Matter is anything that has mass and volume. And we can say what it is. It's state. State meaning solid, liquid, or gas. Composition, so what it's made of, the elemental breakdown composition. So state, solid, liquid, or gas. I know I'm not mentioning plasma. Plasma is just a gas that has been ionized. So plasmas behave quite a bit like gas. And then we can have the change of states as well. So I mentioned states. So we have, generally speaking, 3 states, unless you count plasma. Are there other states? Yes, there is a glassy state that's kind of like a liquid that has a really high viscosity. I already mentioned plasma. But these are the main ones: solid, liquid, gas. So what are the properties? Solids have very set definite shapes and very set definite volumes. Liquids have not set shapes, but they have a very definite volume. Gases have neither set shapes nor set volumes, and that's why I'm kind of linking plasma with gases here, because it fits that definition well. So mention here solids. These are the atoms and molecules. They are very set in where they are, and they don't move very much relative to each other. So then the liquid on the other. So solids. I should mention more here. With solid, you can be crystalline or amorphous. Crystalline solids means that the atoms are in very set shapes. So a perfect diamond, for instance, has that zinc blende crystalline structure. And you can have crystalline many things. I worked with iron single crystals. So you can get iron to sit in a very set crystalline pattern. But it's relatively hard to do. So iron is, if you see iron just sitting out, it's going to be amorphous, which means do not have a very specific order. It is a general order to iron, but it's not a hunk of iron sitting on your countertop or in a nail or something like that is not going to be crystalline. It's going to be amorphous. So amorphous means more generally packed. And although there can be units of crystals inside amorphous substances, but generally speaking, they're not going to be as crystalline as, say, a very beautifully cut diamond. And liquids have a set volume, but they don't have a set shape. So they're liquids and solids and liquids are also referred to as the condensed state. So there tends to be, generally speaking, much more matter in a solid and liquid state than there is in the gas state. So solids and liquids are the condensed state. Solids are very set in their shape, where liquids are not set in their shape. And liquids also flow. So liquid water, for instance, water is strange because we as humans are actually familiar with all 3 states of matter with water. I'm very familiar with solid iron. I'm not very familiar with liquid iron. In fact, I had never personally seen it, and I'm certainly not aware of what iron vapor looks like, iron gas. But water, I'm familiar with all 3 states. But water, some alcohols, I think usually this would refer to ethyl alcohol. Gasoline, these are liquids at room temperature. Olive oil too, that tends to be a liquid. So gases and gases have neither set shape nor set volume. Also, gases are compressible. So solids and liquids, generally speaking, are not compressible. And this is the idea behind hydraulic lines. So your brake on your car, that's a hydraulic line. if you've ever had air in your brake line and you press on the brake pedal, you know that there's something wrong. The calipers don't squeeze and engage the brakes as much. So gases, and why is that happening? Because if you have air in your gas lines, you press on the brake, you're compressing the air that's in the line, and then the hydraulics don't work. So gases are compressible, and this image here with the piston shows solids are not really compressible, but what are gas? Gas is compressible. Okay, so I know there's a bunch of slides on this, but let me explain this forwards and backwards. And I do apologize that we are changing topics quite a bit in the beginning here. So this is the beginning of the semester, and we're starting with material, and we're also changing topics like very, very quickly. Once we get over a new topic, once we start a topic, we're in a new topic already. So, but I want to spend a little time on this picture because it can explain things. I want to explain things forward and backwards. So matter is what things are made of, and let me start with the least general. So we see here we have heterogeneous mixture. So mixtures, and heterogeneous means, so it means different. So heterogeneous, hetero means different or not uniform, so heterogeneous. Water and sand. So sand and water do not mix, and you can see there's clearly solid sand and liquid water. So these are the top is not the same as a bottom. So for instance, milk from a cow is another one. If you ever see milk from a cow, what happens to milk from a cow? It spreads. It separates. There is the cream up top and then the milk on the bottom. So the stuff on the top is not the same as stuff on the bottom, but you can take a heterogeneous mixture like water and sand, you can separate it out into homogeneous mixtures. So homogeneous, sometimes referred to as homogeneous, homogeneous, they're the same, however you want to pronounce it. And homogeneous, they mean that it's uniform. So homo means the same, and let me go with the milk example. So you take fresh milk from a cow, it separates, but when you buy milk in the store, it says pasteurized and homogenized. So the milk on the top of the milk from the store is the same as the milk on the bottom, whereas from a cow it's heterogeneous. The cream's on the top and milk's on the bottom. So in this mixture here, it shows tea, and you have sucrose molecules in water, in liquid water, both all in the liquid stage. And then with that tea, if you took a sip from the top or like took a spoon and took tea from the bottom, you would not notice a difference. So it's uniform. It's homogeneous, it's homogeneous, meaning the same thing. Then let's go back to the milk example. You can take homogenized milk, and then you can break it down to pure substances. So there's two types of pure substances: elements and compounds. So elements, those are, we mentioned atoms before. We know of 118 elements. There might be more. Of those, maybe 92 we find readily on Earth naturally to any appreciable amount. Maybe 93. There's probably about 20 grams of natural plutonium found here on Earth. But generally speaking, we do not see all 118 elements, even the ones like we don't, well, I'm fumbling my words here. We don't see all of the elements all the time in an appreciable amount. We typically see carbon, hydrogen, oxygen, and nitrogen. We see those in large amounts. And also we see quite a bit of silicon on the crust of the Earth, and aluminum, and also iron and nickel in the core of the Earth itself. But on this planet, we see most of the elements, certainly the naturally occurring ones. But I guess naturally occurrings mean terrestrial here on Earth. But we typically only work with a few of them. But anyways, elements, and you can take elements to form compounds. Compounds are combinations of elements in set ratios. So water, H2O, is 2 hydrogen elements to 1 oxygen element. And okay, So we could take things. So with the milk example, so you have the heterogeneous mixture for the milk. You can homogenize it, and then you can break that down into pure substances. So you can take. There's a lot of water in milk. You can take milk. You can break it down into water. You can break it down into different proteins like whey. Protein is a compound. There's calcium phosphate. That's a compound. They have emulsifiers in there too. So some different lipids. So lipids are fats. Those are all compounds. And so we talk about calcium phosphate, the mineral calcium that's in the milk. You have the elements calcium, phosphorus, and oxygen in calcium phosphate. So those are the elements. And there's water. I already mentioned water as hydrogen and oxygen. Okay, so I started off as general. Let me start with specific and move way up. We have elements. So if you understand it better this way, there's 118 elements, and of those 118 elements, we can join them together to form compounds, and compounds are just different combination of elements, and then those compounds, we can mix them together to form homogeneous mixtures, however you want to pronounce it, and the homogeneous mixtures, they are uniform. We can also form heterogeneous mixtures that are not uniform. And most everything we have here on Earth and in the universe in general are heterogeneous mixtures. We humans are heterogeneous mixtures, right? We have skin, we have hair, we have blood, we have bones. These are all different things. Do we have some homogeneous mixtures in us? Yes, we do. We have blood plasma, for instance. We can take blood and we can turn into blood, and we can make blood plasma from that, and that's a homogeneous mixture. So, but generally speaking, we are heterogeneous mixtures, right? So, pizza, one of my favorite foods, is a heterogeneous mixture. Especially pepperoni pizza is even more heterogeneous, right? So, most things we see are heterogeneous mixtures, but they are all essentially made of elements. So, I've mentioned this in my long tirade before. So, we have pure substance as a mixture. Pure substance is made up of one thing, but a mixture is of many different things. And pure substances are either elements or compounds. Compounds are a combination of elements. And the elements, there's 118 of them, and they're made of a specific type of atom. It's because there's only 118 elements. Seeing the pure elements are relatively rare. Do we see it? Yes. You can find it in nature too. You can find gold, for instance, in nature, and that gold is an element. But most things combine to form other things. And so why is this interesting? So let me do another analogy. So the English alphabet, for instance, has 26 letters. So compare that to chemistry. We have 118 elements. Imagine if we had a language that had 118 letters. That would be a very complicated language. And that's the language of chemistry. That's the language of our universe. And also with English, like the letters T and the letter H, they join together to form a different sound. Just like elements, two atoms can come together and they can form things that have completely different chemical properties. For instance, braces. Braces, the stuff you put on your teeth, they're typically made of nickel titanium alloy. Now, quite a large percentage, maybe on the order of a third of people, are allergic to nickel, the metal. But if you mix it with titanium, then the vast majority of people are not allergic to that. So that's an example of how adding two elements together can completely change the properties. And there's many of those examples. Mentioned before, mixtures are either heterogeneous or homogeneous. Hetero means different. Homo means same or uniform. Hetero, I should say, is non-uniform. And heterogeneous mixture is non-uniform. The top is different than the bottom. It's not the same all the way through, where a homogeneous mixture is the same all the way through. Okay, so let's look at this picture. This doesn't look blue to me. It looks Looks white, but hey, that's book says it's blue, so it must be true. So uh, we have a blue circle of one element, and the red square looks like a circle to me. Which of the image is a pure substance? The answer is A, because that's the only one that has the same for both, and it looks like water molecules to me. B looks like oxygen and hydrogen atoms, and C just, or I'm sorry, B is molecules, C is atoms only. Okay, mixtures, and you can separate mixtures. I mentioned with the heterogeneous, so non-uniform mixtures, and there's an easy way, decanting. So I do this not necessarily with water and sand, but I do it with soup. I like to make soup, and then when I make the broth, I'll oftentimes, well, I'll decant, but I'll skim the fat off the top that floats. So that's a very common way to do things in the kitchen and the laboratory. Another one is distillation. So of course this is classically used to make spirits from things like wine or beer, but you can use it to, this is a very common separation technique, is distillation. And that's when you have a liquid mixture and you heat it up, and then you can get the separation of the lighter, more volatile liquid, or the component up the top. And also you can filter things. So if you have a water sand mixture, you can filter out the sand or whatever solid is in the liquid through a filter. So changing topics yet again. Physical change. Well, I guess to explain forward, physical change is something that only affects the physical properties, and chemical changes involve a chemical property changing. And so I know it's a circular argument. Chemical changes involve with an exchange of atoms. So a physical change, the atoms do not exchange in this one. So it only affects the physical properties of something. An example of physical changes are changes of state. So you can take ice from your freezer, you can melt it, and then you can boil it, and you can take the vapor, you can collect the vapor, condense it back down to water, and then you can freeze it back again in your freezer. So what is happening is the water is going from solid to liquid to gas to liquid to solid. These are all changes of state. Does water change at all? No, it does not. Chemically speaking, the water has not changed at all. It is still 2 parts hydrogen and 1 part oxygen. So that is an example of a physical change. Chemical change, though, does involve matter elements exchanging. So iron rusting. So we have a nail here. It starts as iron metal, and then it reacts with oxygen to form iron oxide. And this is a new compound, and therefore this is a chemical change. And so here's a couple examples. We have dry ice here on the top, and this is just changing. This is called sublimation, having solid to gaseous, change in state. And we have sugar dissolving. It looks like sugar dissolving is a physical change. The sucrose sugar is not it's still the number of atoms are still the same. It's still C12H22O11 sucrose. Doesn't matter if it's in the solid form or if it's dissolved in the aqueous water form. This is a physical change only. Then burning propane. So anything that's flammable. This is a chemical change. So propane is being burned, and it's turning into carbon dioxide and water. So we have an exchange of atoms. This is a chemical process, not a physical one. So mentioned this before. I like to talk in terms of chemical properties. Chemical properties involve the exchange of atoms, or it could be lack thereof too. So noble gases are unreactive. That's a chemical property. Gold being unreactive is a chemical property. But most chemical properties are about how things will react. So physical property is something that changes without a change in composition. So well, let's go on. Which diagrams represents liquid water in a pan, and which one represents it's been boiled? So water, so liquid water going to water vapor. This is going to be a change in state, and well, it already gives you away that liquid water is on the left, and boiling water is a physical change only, which means that there's going to be no exchange of atoms, and A is the only one that does not have an exchange of atoms. And changing topics yet again. And this is a chemistry intro definition. Energy is a capacity to work. If you take physics, energy is defined, work is, like I said, work is defined as force times the path length, specifically the integral of the force vector dotted with the ds, the path, the path that it's going. So, energy, we're saying the capacity to work. You have a lot of energy. What does that mean? You could do work. Energy has different forms, but we're just going to keep it very simple. We're going to talk more about energy. Light, for example, is also a form of energy. But work is something that's forced along a path length. So energy, and there's a couple different types. Kinetic energy. So kinetic energy is the energy of motion. Potential energy, this is stored energy. And actually thermal energy is, it's actually a kinetic energy. Thermal energy is actually kinetic energy, but it's dealing with the kinetic energy of atoms and molecules on a very small level. So there's an old classical example where you hold your physics textbook up and say, this textbook has potential energy, and then you let the textbook go, and the textbook slams on the table, wakes up all the sleeping students, said, that potential energy has turned into kinetic energy. So potential energy is stored energy, kinetic energy is energy of motion. So energy can be stored gravitationally, and that's the idea typically behind water faucets, right? So you open up the water tap, and then the water flows out of your tap. How is the water flowing out? Well, they put water towers up really high, and then by gravity has stored potential gravitational energy, and then you open up the tap, and then the water flows downhill. So you can also store energy chemically in form of chemical bonds, and that's where the energy of a donut comes from. So, or food. So if you have a candy bar that has 100 calories, that means that 100 calories is stored chemical potential energy. And you can take that 100 calories and then eat it, and then go and run for a bit. You can certainly do that with the energy, right? So that is the stored energy that has the capacity to do work. So summarizing, it's conserved, but it's either stored or it's in motion, but it's also conserved. So it's law of conservation of energy. And but as you have stored energy and you release it, then it changes forms. But the total amount of energy does not change. Generally speaking, few examples like E equals mc squared, you can change the amount of energy in the system by turning the matter into energy, but that's very, very rare. So what type of energy is chemical energy? Chemical energy is stored energy, and that means it's potential energy. Changing topics yet again. So since I am speaking as an American to most likely an American audience, and we typically use the English or imperial system quite a bit, at least colloquially. In science, typically the metric system is used. And the metric system is an engineered system. And it's very nice because the conversions tend to be a factor of 10. Also, when you do other conversions, especially when you involve heavier math, there's something called a Jacobian. That it's much easier to use metric system when you are dealing with the higher level of math. It's nice to have things in units of 10. So we have a couple base units for the metric system: the meter, the kilogram, the second, the temperature Kelvin, mole, ampere, and although we don't use this very much anymore, the candela, we typically use energy for light intensity now. The other thing, these things are changing. So the mole is based off of carbon-12 at the time I'm recording this video. There's talk of changing that to silicon. Also, the kilogram is being thought about being changed to silicon. Right now, kilogram is based off of a hunk of platinum. And problem with that is that the kilogram is actually changing because it's evaporating. So the kilogram and the mole might change soon. So in the length, the meter, and time are also connected. They're defined now by a meter is defined by how far light goes in a certain amount of time. So meter, I mean I can't show you how long a meter is. It's about I'm 188 centimeters tall. It's about half my height. If you can't, I know you can't see me. It was originally 1/10 millionth the distance between the equator and the North Pole through Paris. But now we have it defined by how far light goes. And mass is the amount of matter, and we have it based off of the kilogram right now. It used to be based off of water. So 1 cubic centimeter of water weighs at 4 degrees Celsius weighs a gram, and 1 liter of water at 4 degrees Celsius is a kilogram. So, but this is probably going to change, and I don't know, relatively soonish. I hope I don't have to record these videos again. They're like, no, I told you. Now it's probably come out that it's been changed to silicon. And difference between weight and mass. Mass is the amount of matter. Weight is the force due to gravity. So if you go to the moon, your weight is about 1/6 of that of the Earth. So does that mean the amount of mass has changed? No. The amount of force that exudes has changed. So weight is a force. So second is the amount of time. And the nice thing about time is that we've all agreed on this. No one has a different, as far as I know of, no one has a different definition of time than the second. So then the unit of temperature is Kelvin, and Kelvin is also referred to at, well, the step of a Kelvin is also the step of a Celsius, and the Celsius temperature is if you take the average pressure of the Earth, Earth's atmosphere, and look at water between freezing and boiling, it's 1/100th of the scale to go from freezing to boiling, and Kelvin is just the absolute. So temperature, the definition of temperature is average kinetic energy, specifically average translational kinetic energy. We'll talk about translational energy later. When you get to absolute zero, it means nothing's moving. You can't have negative absolute temperatures because you can't get any slower than not moving. So remember, it's negative 1/10,000 degrees Celsius. There is no such thing as that level of cold because, like I said, you can't get any slower than not moving. So temperature is just a measure of how fast things are moving in a atomic/molecular level. So if you have cold pizza and warm pizza, what's the difference? The warmer pizza, the molecules are moving faster. So, and also energy, well, thermal energy we can transfer called heat. Heat always flows from hot to cold. So meaning if I have if I hurt my hand and I put ice on it, my hand is high heat. It's got lots of molecules bouncing around, and the ice is colder. The molecules are not moving as quickly when I put the ice pack on my hand. The kinetic energy by collision will knock the energy towards the ice, and then the ice will then increase in temperature. So heat always flows from hot to cold. I mentioned this before, the Kelvin scale, it's the absolute scale of Celsius. It's different than Fahrenheit. There actually is an absolute Fahrenheit scale. It's called Rankine. But with Kelvin, Kelvin's used much more frequently. But notice the other thing is that we have 0 Kelvin. We don't have 0 degrees Kelvin. There's no degree because it's not relative. So degrees Celsius, the degree symbol means that it's relative. So and yeah, lower temperature don't exist, like I mentioned before. It can't get any colder than not moving. So here is the relationship between Celsius and Fahrenheit, and also Kelvin and Celsius. Which temperature scale has no negative temperatures? It's going to be the absolute scale. So Kelvin and Rankine are the ones that we typically use. Okay, so still talking about units and using prefix multipliers. So we have the base units, and then we relate the base units to them to each other. So for instance, the meter is what's used as a symbol as length, but the meter is used to describe really tiny things like atoms and really big things like stars and planets, and of course things in between. So how do we distinguish between them? We have a prefix. So kilo, for instance, means 1,000. So here are the different types. So have the base unit. If you have a tenth of something, deci, then a hundredth, centa, a thousandth, milla, a millionth is micro. Let me keep on going down then. Nano, pico, femto, atto. Then you can go up. Actually, not listed on this. You can have deca for 10 and hecta for 100. Not listed here, but kilo is 1,000, mega, million, giga, tera, penta, and exa. And if you might notice, this is also with bytes in the computer. A kilobyte is not 1,000 bytes. It's actually 1,024 because it's base 2, but it's close enough. But you've probably seen those in other things, and not just science class. Okay, and then we have other units. So volume, for instance, volume is three-dimensional space, so it's length cubed. So a cc, a cubic centimeter, is also a milliliter. A milliliter is a cubic deciliter, and a cubic liter is going to be 1,000 liters. So you can have so that's just so volume is length cubed. Density is mass divided by volume. So and then density also involves something with sinks. If something will sink and float. This is a whole other field, also known as buoyant force. So the buoyant force is described as the amount of matter that's displaced. So for when you're floating in water, for instance, you might notice that the rest of your body is underwater, but then your head is above water because your body is pushing the water out of the way, and then the weight of the water you're displacing. I'm using the word weight, not mass, because weight, this only works in a gravitational field. So the weight of the displacement is then creating the buoyant force. So if you've ever seen hot air balloons, they're very, very large because air is much thinner than water, whereas boats and humans can float, at least most humans can. Like a boat, for instance, it goes underwater, but the amount of water that the boat is pushing out of the way is the weight that causes the buoyant force for the boat to float. So also brings us to intensive and then extensive properties. Intensive property is something that does not matter how much you have. So density is an intensive property. Extensive property depends on how much you have. So let's look at water. So volume and mass, these are extensive properties. So the volume and mass of a spoonful of water. So a spoonful of water is about 5 milliliters, and it's going to have a mass of about 5 grams. A liter of water is going to have, let me give it away, it has a kilogram of mass and it has a liter of volume. And then you have something like Lake Tahoe, which is a huge amount of water, and it has, I don't know what the mass and volume of Lake Tahoe is. It's very large. Those are all extensive properties, the amount. But what is the density of water? Does the density of water change for a teaspoon, a liter, or for assuming that Lake Tahoe is very, very pure? Does the density change? No, it does not. So that is an intensive property. So the density of copper decreases, the temperature increases, which occurs sample copper when it's warmed from room temperature to 95 degrees Celsius. So and so the copper decreases. Okay, so let me think about this. Density of copper decreases, so that means that it's going to expand because the density is mass divided by volume, and if the density decreases, so mass divided by volume, that means that the volume number is going to have to become bigger. So because when you have so with fractions, one number of numerator, denominator, if the denominator gets bigger, the number gets smaller. So density gets smaller. What's going to happen? Either the mass decreases or the volume increases. So either the numerator gets bigger or it decreases. Either the numerator gets smaller or the denominator gets bigger. In this case, we're not losing matter, so that means that the denominator is bigger, which means that the volume is getting bigger, which means the sample is expanding. So I'm going to look at that in terms of fractions. All right, moving on, new topic. Significant figures. So when we report things, we as scientists, we have a way of telling how well we know something, and the way we tell how well we know something is by using significant figures. So the last number and the number of figures is that tells you like what numbers are we sure of and what numbers are we not sure of. And for the number 5.213, we're pretty sure about the 5.21. The 3, we're not entirely certain about that last one. So and this whole unit there has 4 significant figures. So here's the general rule. The non-zero digits are significant, and the interior zeros are significant. So looking at this example, 28.03 has 4 significant figures. 408, the 0 there is significant. And but let's talk about the interiors. We'll talk about the other zeros. So prior to a number, those are not significant. So 0.0032, these zeros here are not significant. But zeros after are significant. So 45.000 is different than 45, because as a scientist, you see the 45.000. That tells us that that these numbers, we are sure that we have that measurement down to that level of accuracy. So right here, this 1200, this is ambiguous. We're not really sure how many sig figs we have. And also, even better with scientific notation, this then tells us, oh, I am communicating directly to you how well we know something. Sometimes if this is written as 1200 with a decimal point after that, that's also communicating I'm sure of these 4 figures. So and so something besides significant figures, there's also exact numbers. So I have two thumbs. Is that 2.000? No, that's an infinite number of significant figures. So those are as an example of an exact number. So the conversion factors we are set to define well, some conversion factors are defined, some are not. So interestingly enough, an inch, if you go by the English imperial system, and an inch is defined as 2.54 centimeters. So it's kind of funny, actually. The definition of an inch is actually metric, but some are set and defined, while others are not. So the pound to kilogram, for instance, is not exact. So using sig figs and calculations, you have to look at them and then determine that through the operation. So you do not lose or gain precision. We should not lose or gain precision during the mathematical operation. So there are rules for that. Come on. Okay. Here are the rules. In multiplication division, the result has to do with the number of the fewest significant figures. So we have a multiplication with 4 sig figs multiplied with something with 5 sig figs multiplied with something with 2 sig figs. The result goes with the lowest number of sig figs, it's 2. Same thing with the division. 5 sig figs divided by a 3 sig fig gives us an answer to the level of sureness to 3 sig figs. For addition and subtraction, the sig figs stop at the point where you're least sure of. So looking at this operation, 2.345 with an addition of 0.07, in addition to 2.9975, we are only sure to the hundredths place, to the second, to 2 places after the decimal point, so we can only report the value knowing the least amount there. And the same rules with subtraction. So this addition and subtraction, you have to look to see where the limit of the measurement is. And rounding, for significant figures, you can either truncate, you can round. Rounding is more common. So, and it's also typically rounded up. So 5 is rounded up to the next unit. Some places it's not typical, but sometimes they round up or down to an even number. So that's also frequently, but more frequently is just rounding up. And for instance, here you can see it's for rounding up 5 or more goes up higher. So 5.37, 7 is higher, is 5 and above, so it rounds up to 5.4. 5.34, 4 is below 5, so it rounds down to 5.3. 5.35, you round up to 5.4. 5.349, I'm sorry, but they are just not at that level. It rounds down to 5.3. So rounding and multi-step calculations. So you do it at the end. So round at the end. So this helps to eliminate systematic errors. So do all the operations and then keep track of the sig figs and then make the decision at the end where the sig figs go. So that's what this slide is saying. Also, definition between accuracy and precision. Accuracy is how close you are, and precision means how close the measurements are to each other, and reproducibility. So if you look at these, you have the different trials, student A, B, and C, and if you look at these, student B is very precise. So meaning the measurements are very close together. That's the definition of precision. And if you go by accuracy, student C is the most accurate, but he or she is not the most precise. So it's important in science to have both accuracy and precision. But you have to pick one. It's better to pick precision, to be honest with you. So you can see here, well, I should, let's see, this, I'm sorry, C is accurate and precise. I didn't look at the data enough. Sorry about that. So student A is neither accurate nor precise. Student B is precise but not accurate, and student C is both accurate and precise. So, and so for chemical problems, for intro chemistry, at least the first semester, first two quarters, most things are unit conversion problems, and you can solve them using something called dimensional analysis. Essentially, you're multiplying by things by 1 over and over and over again, and then you can cancel out the units. So we will go over this quite a bit in the future. We're just setting you up for now. For instance, unit equation here, I mentioned this before, a centimeter is 2.5, I'm sorry, an inch is 2.54 centimeters. And you can use this to convert between the two. And do it by fractions. So with dimensional analysis, you start off with what you know, and then you move over to the right. And essentially, though, as I mentioned before, you're basically multiplying by 1. So having the conversion factor. And so how do you solve problems? Well, you start off, you look at the given information, and then you have to figure out where you want to go. That's the endpoint. So I know what I have, and I know where I need to go, and now you need to come up with, like, okay, then I need a conceptual plan how to get there. And then now you need to strategize. So I'm strategizing how I'm going to get there. What information do I need? What do I don't need? Where can I get this? And then if you set up the calculations properly, what's nice about these is that they all cancel, and as long as you didn't mess up any steps, you should do it correctly. So also a dimensional analysis, look at the number. So for instance, converting between length to volume. So length, but volume is length cubed. Also area is length squared. So you have to do the operations twice. So going from a square inch, in terms of square centimeters, you have to square the 2.54. So a square inch is 6.45 square centimeters, for instance. So involving equations, it's the same idea. Sort, strategize, solve, check. So look to see what you know, look to see what you need to have, and then you think, okay, how do I get there? Then you do it, and then you go back and say, hey, did I do this properly? You check to make sure that you've actually done this properly. So that's the general idea with solving problems in this course. And what else besides problem solving? We're almost done, guys. It's getting close to the end. Interpreting data. We also look at data and then look at how to analyze it. So what are we going to do to analyze things? So let's look at some results. And we have these samples of water. We have 20 grams, 50 grams, 100 grams. We break it into hydrogen and oxygen. Are there any patterns here? Are you seeing any patterns? I mean, looking right away that we always seem to have a small amount of hydrogen, and we have a lot more oxygen than we have hydrogen. Also, of course, you notice that they equal. That when you add them together, you get the mass of the water. That's the mass of conservation of energy, the law of conservation of energy. That makes sense, but we're seeming to consistently get the lower amount of hydrogen and a higher amount of oxygen. Even further, it seems to be in about a 1:9 ratio. It seems it's about 1 part hydrogen to 9 parts oxygen. So that seems to be consistent throughout. So, I'm sorry, 1 to 8, excuse me. 1 to 8, sorry, not 1 to 9, sorry. But it's not exact. It's about that. Okay. What else can we do? We can look at graphs. So we use graphs quite a bit in science, and we also look to interpret graphs. So let's look at this graph here. And we have the y-axis and the x-axis. So the x-axis is known as the independent variable. The x-axis just goes. The y-axis is the dependent variable. It is a function. The y-axis depends on the value of x. And so in this case, the amount of carbon dioxide in the atmosphere, concentration, depends on the time, on the year. So that's how we interpret this graph starting off. And then now we're going to start, so besides the independent and dependent variables, what do we notice about these graphs? Well, we have a number of values. So the years, of course, we're using the years starting in the year, 18, I guess this would be, 1855, I guess. No, it's 1850, excuse me. That's 1850. And the concentration also does not start at 0, it starts at 290. So if it actually started at 0, this graph would be much higher. So notice that here that the number values also change on the graph. Same thing with the year. We're not starting with year 0, we're starting with the year 1850. And we're also not starting at 0 concentration carbon dioxide, we're starting at 290. So then when you look at the graph, certain things to look for. One of them is the concavity. So this is concave up. This is going up. Versus concave down. Concave down would have this downward look. Then also the slope of the line. So if you look at the slope here, this is a small slope, and then this slope is increasing, and this slope is going really high. That means that the rate is going higher. So the rate of this is increasing versus exponential decay. So as I'm recording this, I'm in the midst of a pandemic, and I get nervous when there's exponential growth, and I get excited when there's exponential decay for the number of cases in the pandemic, for instance. So this is the way to look at some of these graphs and interpret them. So remember that we have the x-axis that have the independent variables, the y-axis with the dependent variables, and then looking at the data, there's certain things like the concavity and the rates. The rates being the slopes. It tells you what direction things are going. This direction is going, it means that the rate is increasing as they're going through. And I already mentioned the numbers here. And what would happen if the y-axis began at 0? Well, this would just be a taller graph, and it would also be harder to see. So this is also for presentation purposes. And the rate is the slope of the line. So the rate is increasing. And we're done.